So now that we know how to represent a probabilistic model with a Bayes net, how can we use that Bayes net to conduct inference and answer questions? In the next few slides, we'll illustrate inference by enumeration in a Bayes net. So in the general case, we have some evidence variables, E1 through Ek. We also have a query variable, and that's the variable that we're trying to get information about. That's the variable we're trying to guess. We may also have some hidden variables, h1 through hk, and these variables are not directly observed, but they somehow come into play in the Bayes net. We are usually looking for the distribution of Q given some values of the evidence variables. So let's go back to our alarm network to illustrate inference by enumeration. If you remember from that Bayes net, I have two neighbors, John and Mary. So let's say that I'm sitting in my office and I see two missed calls, one from John and one from Mary. Now that worries me. I just wonder if there was a burglary at my house, and that's why John and Mary called. So what is the query here? The query is the burglary, right? This is the random variable that I'm wondering about. Was there a burglary at my house? And the evidence here is the fact that John and Mary called. So J and M are my evidence variables. I did not actually talk to them. All I know is that they called. Now, there are also some hidden variables here. I don't know if the alarm went off, and I don't know if there was an earthquake. So E and A here are my hidden variables. So what probability are we looking for here? I'm just wondering if there is a burglary at my house, given that John and Mary called. So we're looking for P of plus B given plus J plus M. So let's go ahead and compute P of plus B given plus J and plus M. By definition of conditional probability, this is equal to P of plus B plus J plus M, the joint probability, divided by the probability of plus J and plus M. This is simply applying the definition of conditional probability. We also know that if we have a distribution that involves x and y and we want to compute the marginal probability of x, we basically have to sum over the values of y. So p of x is equal to p of x plus y plus p of x and minus y. So let's apply this to p of plus b plus j plus m, to this joint probability. We want to introduce the hidden variables a and e here. So let's introduce the hidden variables one at a time. So let's first introduce e. So we apply this where our plus y is plus e and minus y is minus e. So we just introduce e as a variable here. We're saying that this marginal probability is equal to the sum over the two values of e. And then for each one of these, we introduce the variable a. So we say that p of plus b plus j plus m plus e is equal to this sum here. So we introduce plus a, and we add plus a and minus a. And then we do the same for this part here. We introduce a, so we have to add the two joint probabilities for plus a and minus a. So now we have that. We know that this joint probability is equal to the sum of four terms. Where can we go from here? So let's compute the first term. This is a joint probability. We have a Bayes net here, and we know that Bayes nets allow us to write a joint probability as a product of the local probabilities. So here, this joint probability can be written as P of plus B, B has no parent, times P of plus E, E has no parent, times P of plus A, conditioned on the parents, plus B and plus E, times P of plus J, conditioned on the parent, times P of plus M, conditioned on the parent. So we know that because we have a Bayes net. And now we can read each one of these local probabilities from the table. So P of plus B is 0.001. P of plus E is 0.002. P of plus A given plus B and plus E, we have to go to this table here, and it's 0.95. P of plus J given plus A is 0.9, and P of plus M given plus A is 0.7. And we can just plug in the numbers and compute the result. We do the same for P of plus B plus J plus M plus E minus A. It's also a product of the local probabilities. We just have a different value for A, and we read the values of the table, and we have the result. We do the same for minus E plus A, P of plus B plus J plus M minus E plus A. We read the results and compute the product. And finally, we do the same for P of plus B plus J plus M minus E minus A, and we have the result here. So now that we have computed these four terms, we can add them together, and they give us this joint probability, P of plus B plus J plus M. We can do the same to compute the probability that there's no burglary, given that John and Mary called. So this conditional probability is equal to this joint probability divided by the probability that John and Mary called. And then we do the same for this joint probability. We introduce the hidden variables, and we get these four terms. We compute these four terms just like we did before when we had plus B. And this is the result I got. You can do that and verify that you get the same result. So now that we have P of minus B plus J plus M and P of plus B plus J plus M, we have these two joint probabilities. What we're really interested in are the conditional probabilities. So we want to compute this conditional probability and this conditional probability. To do that, we still have to divide by P of plus J plus M, but we can use our normalization trick. So we know that these two probabilities have to add up to 1. So we compute the sum of 0.001492 and 0.000592. We add them up, and then we divide. So P of minus B given plus J plus M is equal to this amount here divided by the sum, and P of plus B given plus J plus M is equal to 0.000592 divided by the sum. So here, instead of computing P of plus J plus M, we are normalizing. In fact, when we compute the sum to normalize, we are actually computing P of plus J plus M. Because if you look here at these two numbers, what we have is P of plus J plus M minus B plus P of plus J plus M plus B. So here we are computing the marginal probability of plus J plus M, and we are summing up over the values of the B random variable. So whether we normalize or whether we compute this, we're actually doing the same thing. And these are our results. So even though both John and Mary called me, there's still less than 30% chance that there was a burglary at my house. So maybe they just both wanted to chat. So in summary, today we've seen that Bayes nets compactly encode joint distributions. There are some guaranteed independencies that can be deduced from the graph structure. Inference by enumeration is the basic exact inference method for Bayes nets. It's a bit tedious. There are some techniques, such as variable elimination, to make it more efficient. There are also some approximate inference methods for Bayes nets that include randomized sampling.